All right, today we're going to crack open the Physicist Toolkit. We're going to figure out how to understand and even predict motion, from the super simple to the stuff that looks totally chaotic. It's all about building a new way to see the world, just like a physicist does. Take a look at this classic puzzle. You've got a ladder sliding down a wall. You think, hey, it's just a ladder sliding, right? But the top is moving straight down and the bottom is moving straight out. And every single point in between is tracing its own unique curving path.
So how in the world could you predict that? How could you know the exact speed of the ladder's middle point at any given moment? It seems really complicated. But guess what? There's a method to the madness. Engineers have a whole set of powerful tools to nail down exactly what's going to happen.
Okay, so the very first tool we need isn't some complicated formula. It's actually a language. It's the super precise vocabulary we use to describe any kind of motion, and it's called kinematics. This is all about the what, the where, and the how fast. So this whole language really boils down to three key ideas. You've got displacement, which is just, where did it go? Then there's velocity, that's how fast is it going and in what direction? And finally, acceleration, which tells us how that velocity is changing from moment to moment.
Now here's where it gets really cool. These three ideas aren't just separate concepts. They're all deeply linked together through the mathematics of change, calculus. If you know an object's position over time, you can figure out its velocity. And from its velocity, you can find its acceleration. And even better, it works backwards too.
And you can actually see this connection in action when you look at graphs. If you have a graph of an object's position, the steepness of the line, the slope, at any given point, tells you its exact velocity at that instant. And it works the other way too. The area underneath a velocity graph tells you how far the object has gone, its displacement. So the crucial point here is that these graphs are hiding information about each other in plain sight. It's like they're talking to each other. You just have to know how to listen. Once you get these relationships, you can flip between position, velocity, and acceleration without a ton of messy algebra.
And this isn't just about pretty graphs. When we bring in the math, this language becomes incredibly powerful. I mean, look at this. Even if an object's acceleration is constantly changing, which happens all the time, we can use the tools of calculus to work backwards and figure out its exact speed and location at any point in the future.
Okay, so we've described how things move, but that's only half the story, right? The big question, the fundamental question is why? Why do things move or change their motion in the first place?
Right, so if kinematics is the description of motion, our next tool is the explanation. We're moving from the what to the why. And it all starts with a simple question. What makes something accelerate?
And the answer, in a word, force. This is Newton's second law, and it is arguably the most important equation in all of classical mechanics. It's the direct link between the pushes and pulls on an object, the forces, and how its motion changes. You push harder, you get more acceleration. The object is heavier, well, you get less acceleration for that same push. Simple as that. Okay, so to actually use this law, physicists and engineers have this awesome little trick called a free body diagram. It sounds fancy, but it's just a simple sketch. You isolate the object you care about and draw arrows for every single force acting on it. Gravity, friction, you name it. It's the first step to clearing up the chaos and solving pretty much any problem involving forces. Now, let's talk about a force you deal with literally every second. Friction. It's that force that resists motion. And without it, you couldn't walk, cars couldn't drive, the world would be a very slippery place. But friction is, well, it's kind of weird. It's not just one number. As you start to push on something, a static friction pushes back, growing to match your force and keep the object still. But once you push hard enough to break it free, it starts sliding. And suddenly, the kinetic friction fighting you is actually weaker. That's why it's always harder to get a heavy box moving than it is to keep it sliding. Okay, so now we have a tool to track all the forces and accelerations moment by moment. But sometimes that's just the long way around. So let's grab our third tool, which is a total game changer. We're going to look at the problem from a totally different and honestly more elegant angle, through the lens of energy.
And the difference between these two methods is huge. Think about it like this. The force method, F equals ma, is like watching a movie frame by painful frame. It tracks every little detail. The energy method, though, it's like skipping right to the final scene. It doesn't care about the messy middle. It just connects the beginning state directly to the end result.
This all comes down to something called the principle of work and kinetic energy. Just think of work as energy being transferred into or out of something by a force. And this principle is basically an energy accounting rule. It says that the total work you do on an object equals the change in its energy of motion. It's kinetic energy.
Now, look at this setup. This is where the energy method just absolutely shines. If you try to use F equals ma here, you'd be writing equations for each block, worrying about the tension in the cables. It would be a total headache. Totally doable, but really tedious.
But with our energy shortcut, we can just bypass all that mess. We don't have to care about those internal forces like tension. We just look at the whole thing as one system, calculate the work being done by gravity and friction, and bam, it tells us the final speed of everything. It's so much cleaner.
All right, let's take a step back. We've just loaded up our toolkit with 3 incredibly powerful tools. We have kinematics to describe motion, Newton's second law to explain why it happens with forces, and the work-energy principle to get a bird's-eye view using energy. So, how do you know which tool to pull out of the box? Well, it's simple. If a problem gives you acceleration and asks for speed or distance, think kinematics. If you need to find the specific force, like how tight a rope is, you've got to use F equals ma. But if the question is all about the final speed after something is moved a certain distance, especially in a complicated setup, the energy shortcut is almost always your best.
And that's really the secret, isn't it? The real genius of physics isn't about memorizing 100 different formulas. It's about having a deep understanding of just a few fundamental tools and then building the intuition to know which one is the right one, the most efficient, the most elegant for the job at hand.
So there you have it, the Physicist Toolkit. We've got the language, the laws, and the shortcuts. But the real question is for you. With these new tools in your head, what everyday motion are you going to look at and see in a completely new light?